So welcome to the second of my videos on titration course for level 3 aqueous systems. This video is going to be entitled titration tricky titration questions. It's even difficult to say, because what we did in the first video was we went through the standard theory that you would get for your titration curve questions, but there are some that they put as part C questions which are quite tricky. I may not be able to write all the answers and show all my workings on this question paper, so what I'll do is I'll have a second page open, I'll do my workings there and transfer my answers back to here. So we need to read the question here. Aqueous systems, question 1a, 0.1 mole per liter of sodium hydroxide solution is added to 8 ml of 0.1 mole per liter hydrochloric acid in a titration experiment. So just to draw a little diagram to show what we're doing there. I'll put it on the side here because it will fit nicely. You have a burette, and in the burette you have your sodium hydroxide, that's your strong base, and its concentration is 0.1 mole per liter. In the beaker, or maybe it's a conical flask, you have 8 mils to start with of hydrochloric acid, and its concentration is also 0.1 moles per liter. So that's the starting situation, and to that 8 mils of acid you're going to add 8 mils of sodium hydroxide. Now the assumption here is added to, so 0.1 mole per liter solution is added to 8 mils, so they haven't told you what volume has been added yet or anything like that, so we need to just ignore that for a second. So the first question is, what is the pH of the original acid solution? So the pH of this solution here before any base was added. So what we're looking for here is, I'll just write down the chemistry for what's happening. So you have your 8 mils of acid, HCl, and there's no sodium hydroxide present yet. So what you have in that solution is simply the full dissociation of the strong acid to give you hydronium ions plus chloride ions. The starting concentration of the strong acid is 0.1 mole per liter. And so, because it's a monoprotic acid, one proton for the acid, you're going to get the same concentration of protons per mole of molecule. So you get 0.1 moles per liter of hydronium ions, and so the pH is just simply found as minus log to the base 10 of that, which works out to be a very low pH of 1. So your starting pH for this system is 1. Now the next question they have, so the answer to that was pH of 1. Next question they have here is, what is the pH of the final solution when 16 mils of sodium hydroxide solution has been added? So you add 16 mils in total from this burette to complete the titration. So this is the volume that's been added to get the final pH of the system. So it's going to be strongly basic. We know that much from our understanding from the first video. This, by the way, this first question is a strong acid, strong base titration. So if I go back to my rough work page here, the second question then, so this is question 1a, and that was part 1. Part 2 is asking us for the final pH after 16 mils of sodium hydroxide added. So the key to this question is to consider the dilution factor which is taking place. Basically, you have a beaker. In your beaker, you had your 8 mils of your HCl to start with, and into that now you've now added 16 mils in total of your sodium hydroxide. So we now have 16 mils of sodium hydroxide. So the total volume now of this solution is equal to 24 mils. So there's a dilution factor of the original 0.1 mole per liter concentration of sodium hydroxide. We also need to make the point that the first 8 mils of sodium hydroxide added neutralized the 8 mils of HCl, so that would have been at equivalence. So therefore there are 8 mils of sodium hydroxide left over, or additionally added, and these will account for the final pH of the solution. So the first 8 mils neutralize the 8 mils of acid, and then the additional 8 mils added, they are what accounts for the final pH of the solution. So you take the original starting concentration of the sodium hydroxide, which was 0.1 moles per liter, and that has the 8 mils of that, which was needed for the final pH, the 8 mils which were additionally added after equivalence, have been diluted into a total volume of 24 mils. So that concentration becomes 0.033 moles per liter. So that's your final concentration of hydroxide ions. And then, of course, we just do the conversion to concentration of H3O plus using the dissociation constant for water. So 1 by 10 to the minus 14 divided by 0.033 moles per liter. And that gives you a concentration of 3.03 by 10 to the minus 13 moles per liter. And that's your concentration of H3O plus at the end of this titration, which is a very high pH of 12.5, as you would expect for a strong base. Let's return then to our question sheet. So the answer to this was 12.5, pH of 12.5. We're building up some pH values here which are going to help us to draw a titration curve for this titration in a few minutes. The next question is, what is the pH of the solution at equivalence point? Well, for a strong acid, strong base, the pH is always 7, because you get equal concentrations of hydroxide ions and hydronium ions, and they set up that equilibrium and form water. So this is a pH of 7. And then there's one other thing I wanted to talk about, which was, how do you work out the equivalence volume? So although the question is making the point that the equivalence volume, in this case, the equivalence volume is 8 mils, how do you work that out if you're not told it? Or especially for a weak acid situation where you can't assume that equal volumes of the same concentration of base and acid will be required for neutralization. So the way you do this is you start with what you know. At equivalence, the equation or the chemistry which is taking place is your strong acid neutralized with your strong base to form NaCl, the salt, plus water. From this equation, we can then say that the moles of HCl will give us the moles of sodium hydroxide at equivalence. This is at equivalence. So the moles of HCl can be calculated by taking the concentration and multiplying it by the volume, which was in the beaker. So that was 0.1 moles per liter for the HCl multiplied by 0.008 liters, which is 8 mils. That was what was in the beaker to start with. That will give you an amount in moles of 8 by 10 to the minus 4 moles of HCl, which is also equal to the moles of sodium hydroxide that need to be added for neutralization. So the moles of sodium hydroxide will also be 8 by 10 to the minus 4 moles. And then finally, to get that volume, the volume of equivalence or at equivalence will be equal to the moles divided by the concentration, which is 8 by 10 to the minus 4 moles, divided by the concentration 0.1 moles per liter, which gives you a volume of 8 ml. So the equivalence volume is 8 ml in this case. Okay, so if we go back to our questions, the last thing we need to do is point 4 here, sketch the titration curve on the following graph axis. All right, so we need to use the numbers that we have. The first number we have is the starting pH of 1. So use a highlighter pen here. So starting pH of 1. So we go to our axis. So we're going to have to label these axes. So I just put pH of 1 here. 2, 3, 4, 5, 6, 7 is going to be useful to us. 8, 9, 10, 11, 12, 13. And 12 is about there. Okay, on the x-axis, so the y-axis has pH. On the x-axis, this is volume of sodium hydroxide that we're adding, and that's in milliliters. 8 should be about halfway there, 8 ml, and then 16 ml was useful as well to us. So the first value, as we say, is starting pH of 1. So we've got that there. This is the starting pH of your strong acid, HCl, strong acid. Okay, and then the next thing we can look for is the final pH of 12.5, so we can stick that on our graph as well. So 12.5 is going to be about here. I'll just take a little line across to help us with the drawing. So 12.5, because we need that for our final pH after 16 mils have been added. The starting pH is going to be along here. The equivalence volume we also just calculated was at 8. So that's there all the calculations we can do. The equivalence pH is 7. We have that as well. We can put a line across like this too, which will help us with our drawing. So the final thing now is just put the trend in as best as possible, and to remember that a strong acid-base titration, there's no buffering section, so it's just going to be a nice flat line for the addition of the strong acid. Then when enough base has been added for equivalence, we start to get the equivalence section, and then it turns off as the equivalence is overcome and the strong base dominates. So there we go. I'm happy with that. That would be the titration curve based on the data that we just calculated. So that's how you do that first question. As I say, plenty of detail, tricky aspects to it, and that's the kind of stuff you need to make sure you can do if you're looking for excellence on your titration curve questions. Now the next thing we need to look at is a weak acid strong base. So this is a weak acid strong base situation, and in this case there's probably enough space here to do my 3 calculations on the page here. So I'm just going to divide this page up into three sections, because the 3 things that you need to do for this question. Using a different color pen, sketch the graph curve if the experiment was repeated using 0.1 mole per liter ethanoic acid instead of hydrochloric acid, and circle the buffer zone. Calculate the initial pH and then the buffer pH. That's the hint that we're given here. So there are three pieces of information you need to know here. You need to know the starting pH, just like we did before. So the starting pH of the weak acid, that's the first calculation we're going to have to perform. We need is the equivalence point volume. Okay, and then the third point we need is we need the pH, number 3, we need the pH at equivalence. And as you saw in the first graph, when we had those 3 points, then we were able to draw a trend for the curve. So the first thing here is starting pH of the weak acid. Well, the weak acid here is ethanoic acid, comes up again and again. So at the beginning, we only have ethanoic acid present. So ethanoic acid is set up its little equilibrium with water. And the only species we have are ethanoic acid plus water, its conjugate base ethanoate plus hydronium ions. The Ka expression can be written as before. The products times each other over the reactant, excluding water. And then we rearrange that expression to get the concentration of H3O plus isolated, which becomes that. Remember, we're making the assumption that these 2 species at equilibrium have equal concentration. So the concentration of H3O plus works out to be 1.32 by 10 to the minus 3 moles per liter. And that gives you a starting pH of 2.9. So that's what you would expect for a weak base, a weak acid. It was 1 for the HCl, 2.9 for the ethanoic acid. So we've done one of the 3 things. The equivalence point volume, very similar calculation to before. You need to look at what you know. So at equivalence point, the weak acid is reacting with the strong base, and the strong base is completely converted all that weak acid into its conjugate base, so sodium ethanoate plus water. So we are assuming now at this point that we have equal amounts of the weak acid and the weak base, so 1:1 ratio. So the moles of ethanoic acid, can be calculated by taking the concentration, multiplying it by the volume, so that's 0.1 moles per liter and the starting volume is the same. It's the same experiment as on the top. We just switch the acids out, so it's 0.008 liters, and that gives you 8 by 10 to the minus 4 moles, which is exactly the same as before. The moles of sodium hydroxide can be calculated or related to that because it's a 1:1 ratio from the equation at equivalence point. So the volume of sodium hydroxide, if you take the moles and divide it by the concentration, that's 8 by 10 to the minus 4 moles divided by the initial concentration of the sodium hydroxide, and that gives you an equivalence volume of 8 mils. You can also say from this that the mid volume will therefore be half of that, so that will be 4 mils. So we've obtained two pieces of information from this particular step. We have the equivalence point volume of 8 mils, and we have the midpoint volume of 4 ml. So they're going to be two useful points as well to help us draw a graph. Now the last thing we need is the equivalence point pH, and the equivalence point pH can be calculated using the Ka for the weak acid. So the key to doing this last point is to be able to write both equations which illustrate what's happening at equivalence point. There's always two equations, whether it's a weak base or a weak acid. You should be writing two equations to explain what's happening at equivalence. So we had the first equation before. All of the weak acid has been converted into conjugate base, sodium ethanoate, plus water. Now this would suggest that the equivalence pH should be 7 because you've neutralized the system, but you need to remember that the sodium ethanoate, so the ethanoate from the sodium ethanoate further dissociates and sets up an equilibrium with water of its own, and that forms CH3, so ethanoic acid, plus OH minus ions. So with the presence of these OH minus ions, we know that with a weak acid, strong base titration, it should be slightly basic at equivalence. And we need to therefore calculate the pH now, and the pH should be slightly basic. What we can do here is, because this is a weak base now, this is essentially a weak base equilibrium, and we can write a Kb expression. And the Kb expression for this system would be the products times the OH minus ions over the ethanoate. Okay. Again, the weak acid and the strong base, their amounts are equivalent because all of the strong base has neutralized the weak acid. So therefore, you can say that those concentrations are equal, in which case the expression becomes the square root of Kb times the concentration of ethanoate equals the concentration of OH minus, and that works out to be the square root of 5.75 by 10 to the minus 10. If you're wondering where I got this number, it's the Ka value, 1.74, and then divide that from 1 by 10 to the minus 14. We've done this before, and that will give you the value down here. 5.75 by 10 to the minus 10, that's the Kb value, multiplied by the concentration of the ethanoate, which in this case, at equivalence, all of those concentrations are equivalent, so it's 0.1 mole per liter. And that gives you a value for hydroxide ions of 7.58 by 10 to the minus 6. And then if you convert that to H3O plus and get the pH works out to be 8.9, which is slightly basic. And of course, the midpoint pH can be calculated from that by dividing it by 2. You get half the equivalence pH, which works out to be 4.45. Okay, so we have a midpoint pH, we have equivalence pH, we have a midpoint volume, we have equivalence point volume, and we have the starting pH. And the final pH is going to simply be the same as before, and the final pH is going to be 12.5 because we're using the same strong base. So now we got to try and draw a graph for this one. So let's use a different color. Let's use a pinky color. So our starting pH, 2.9. So 2.9 is going to be around here. So that's 2.9, and that's our starting pH of the weak acid, ethanoic acid. Okay, the other thing we found was equivalence was also at pH or at volume 8, and that the midpoint came up at volume of 4 mLs. This is the midpoint volume. The equivalence pH we just determined was 8.9, so this is 8.9. We draw a little line over just to help us with our graphing. So we know that equivalence should be about there for the weak. So this is equivalence for the weak acid. This was equivalence for the strong acid. And then we also need to put down the pH for the midpoint pH, which was 4.45. So 4.45, let me see, 3, 4, 3, 4, 5, 6, 4. 4.45 is about here then. We draw a line over, and that should tell us that our midpoint should be right there. So that's our midpoint. It's our midpoint. So we have enough points now to draw this graph. So here we go. I get a different color now. Let's use a green. Okay, so starting pH. Now there's initial jump. There is an initial jump. We've talked about that before. Buffer zone. Then we reach equivalence all the way up, and then it tapers off into the final pH. So that would be your buffer zone right there. That's your initial jump. Your equivalence pH is up here, and then your final pH is here. So they're great questions to practice. If you can do those types of questions, you can do the trickiest questions you get on your exam papers. I'm just going to, for completion, I'm just going to cover the other side of this worksheet. This worksheet then continues on to a weak base strong acid titration, so the third type of titration curve. There's a little question here, part C from question 1. Indicators are themselves weak acid conjugate base systems and have their own pKa values. Suggest a suitable pKa for an indicator to use in the HCl titration. Well, the HCl titration, the equivalence pH was 7, so if you use something from 6 to 8, that'll cover that. And then for the weak acid situation, the pKa was 8.9, so if you use something from 7 to 9, that would cover that, suitable indicators. So the weak base strong acid situation, 0.1 moles per liter of HCl is added or are added to 8 mils of ammonia in a titration experiment. What is the initial pH of the ammonia solution? So there are two ways that you could do this. You could look at the equation first of all, ammonia. So before any acid is added, the only thing you have is the ammonia dissociating into water. So you could say that the concentration of hydroxide ions would be equal to the concentration that you started with for ammonia, which is 0.1 moles per liter. Per liter, you could get the concentration of H3O plus for that using 1 by 10 to the minus 14 divided by 0.1 moles per liter, and that gives you a concentration of. So just to correct myself there, it sounded like a good idea initially. It's an example of a teacher making a mistake. When you write that equation out, of course, you can't get a concentration for H3O plus because there's no H3O plus present in the system to begin with. The NH4 plus could further dissociate, but this doesn't seem to give you the same answer as the final answer. So I'm going to scratch that idea. I'm going to do it using the Ka value that you've been given in the question. So from the Ka, you can get a Kb value because this is a weak base that we're talking about. And the Kb value for NH3 is equal to 1.75 by 10 to the minus 5. The Kb expression based on the equation over here is going to be the concentration of ammonium times OH minus over the concentration of ammonia, and then you rearrange that and you get an expression, the square root of Kb times the concentration of ammonia will give you the concentration of OH minus which works out to be 1.32 by 10 to the minus 3 moles per liter. So that gives you a concentration of H3O plus of 7.58 by 10 to the minus 12, which gives you a final pH of 11.1, which is not the same pH that you'd get if you did it this way. If you did it this way, you'd get a value of 13, give you a pH of 13, which is not right. So the final pH we know for this graph is 11.1, or the initial pH is 11.1, so this is a weak base titration we're doing. Part 2, what is the pH after 4 mils of HCl has been added? Well, 4 mils is equal to half the equivalence volume. And at half the equivalence volume, we can say that we are at the, i.e. at the midpoint. And if you're at the midpoint, then there's an expression we can use here where the pH of the system is equal to the pKa of the acidic species. In this case, i.e. NH4+. So we're at the midpoint. The pH of the system is equal to the pKa of the acidic species at this point. So we can simply say that the concentration of H3O+ is going to be equal to the Ka, which is equal to 5.70 by 10 to the minus 10, and therefore the pH is going to be equal to 9.2. So that was an easy calculation. So we have the starting pH, we have the midpoint pH. Now what else do we need? What is the pKa of a suitable indicator for this titration? Well, pKa needs to be, indicator needs to be plus or minus 1 pH unit, so you could go from 8 to 10. Any pKa which is from 8 to 10 should be suitable. And then sketch the curve on the graph. So this is a weak base strong acid titration. So here we go. So we have a just made a mistake there as well with the pKa for the suitable indicator. So I need to address that issue. So the reverse scenario for a weak base strong acid titration. In this case, the equivalence pH is going to be half the midpoint pH. So that's going to be half of 9.2, which is going to be take you down to about 4.3. So 4.3 will be your midpoint. 4.35 will be your equivalence pH. So you need an indicator with a pKa of anywhere from 4 to 5. Should be a good pH indicator for this equivalence point. So the equivalence point pH is about 4.35. And we have everything except the final pH of the system. So before I do part 4 here and sketch the curve, I just want to work out the final pH of the system, which is the question down here, part 3. So you need to consider the total volume at the end of the titration. The total volume at the end of the titration is you've following the exact same procedure as before. It says down the bottom here, you've added 16 mils of acid in total. So the total volume is 16 mils of HCl plus your original 8 mils of ammonia, which gives a total final volume of 24 mils. And therefore, there's a dilution of the acid at the end. There's a dilution of the acid. The concentration of the HCl that's remaining, you've 8 mils of unreacted HCl. The first 8 mils were used to neutralize the ammonia at the equivalence point, and then the remaining 8 mils have been diluted into 24 mL. So the starting concentration of the acid has been diluted, and therefore the final concentration of H3O plus becomes 0.0. So the final concentration of H3O plus becomes 0.033 moles per liter, and that gives you a pH final of 1.5, which is slightly above what the pure HCl would be. So we have a series of numbers here now. We have a starting pH for the weak base was 11.11. So let's use a blue color for this. So we had 11.11. So we're going to put that in our graph now. So we want to go about halfway. This is going to be 8 ml, just like before. 16 mLs here. 1, 2. So pH 1, 2, 3, 4, 5, 6, 7. 11 is here. Okay. So the starting pH of 11.1 is right here. So this is the starting pH of your ammonia, the weak base. Okay. Then there's going to be a drop in pH. And that drop goes as far as the midpoint pH, which we worked out to be 9.2. So we better mark in our 9.2. So 789.2, that's about here. Okay, so we know our midpoint lies along that line. The midpoint volume is going to be half of the equivalence volume, so that's 4 ml again. So the midpoint is exactly there. So that's the midpoint. The equivalence pH we worked out to be 4.43. So 4.43 is the equivalence pH. So that's slightly acidic. So 1, 2, 3, 4, 4. It's about here. So this comes all the way over to the 8 mil mark. And that was our equivalence point. Equivalence point pH. Okay, half the midpoint pH in this case. And then our final pH we just worked out here at the bottom was 1.5. So final pH of 1.5 is here. And then we bring that all the way over. And that's at the 16 mil mark. So if we can put our graph in now in a different color, let's use this color here. So there's a drop, and then you reach the buffer zone. Equivalence pH is here, and then we reach the final pH, and then the graph finishes itself out like that. So we have the drop in pH. We talked about this in my previous video. We have the buffer zone, which is right here. We have the equivalence pH, which is here, and then this is the final pH right here. So even having done those questions before myself and going through them again this morning, I still have some difficulties in places because conceptually there's a lot going on. But if you can do those calculations, you should be able to do any calculation you get on your titration curves for aqueous systems.